Ever feel like finding the absolute best solution to a problem? You know, it's like searching for like a needle in a haystack.
Oh, yeah.
Well, imagine having this powerful magnet that could just like pull that needle right to you. That's kind of what adiabatic quantum computing could do for training neural networks.
Hmm.
AQC, we'll call it for short. But we're taking a deep dive into a research paper today all about that called Training Neural Networks with Universal Adiabatic Quantum Computing. Quite a mouthful.
It is. Yeah, it's a fascinating paper. It really gets to the heart of why training neural networks can be so challenging in the first place.
Yeah, and the authors, Abel, Criado, and Spinowski, they point out that, we often rely on these incredibly tiny adjustments to a neural network's parameters, they call these weights and biases, to kind of nudge it towards the best solution.
Yeah, and the thing is, the problem is, those tiny adjustments, they create this massive, complex landscape of possibilities. And it's so easy to get stuck in a locally optimal solution, you know?
Okay.
It's like, think of it like being in a valley and thinking you found the lowest point. But there's actually an even deeper valley just over the next hill. You just, you can't see it from where you are.
Okay, so you're saying it's easy to get stuck in a rut and miss the truly best solution.
Exactly.
And the authors of this paper are suggesting that there might be a more kind of elegant way to navigate this complex landscape using quantum computing.
Precisely, yeah. The paper really focuses on this idea using ATC to find those global minimums,
Mm.
those truly optimal solutions much more efficiently. And what's really interesting is that they suggest a way to potentially simplify the whole process by rethinking how we even represent information in neural networks in the first place.
I'm intrigued. How does that work?
So typically, we use continuous values for those weights and biases that we were talking about, meaning we're looking at a whole spectrum of possibilities, right?
Yeah.
But these researchers, they propose using discrete values instead.
Okay.
It's kind of like, how do I want to, it's like the difference between, if you're painting and you can blend every shade of blue imaginable
Right.
versus working with like a limited palette of distinct blue hues,
Okay.
you might assume that infinite spectrum gives you more options, right?
Right.
But what if you could achieve the same or even better results with a simpler, more targeted approach?
That's a really interesting way to think about it. So instead of fine-tuning with all these tiny increments, we're talking about making more strategic leaps towards the optimal solution.
Yeah,
Okay, and that's where AQC comes in.
exactly.
So it's like having a map that guides you directly to the lowest point in that complex landscape, avoiding all the detours and dead ends.
Precisely.
So how does this AQC actually work in practice? The paper mentions something called the polyspin method. What is that all about?
Okay, so the polyspin method, it sounds kind of technical. How does that play into using AQC to find these optimal solutions?
So imagine, right, you're trying to find the lowest point in a landscape. But instead of a regular landscape, like picture it's constantly shifting and changing, like really hard to get your bearings. Yeah. I mean, you'd be stumbling around, never sure if you were really at the bottom.
Exactly, exactly. That's kind of what traditional neural network training can feel like. It's like, you're never really sure. But AQC, it offers this smoother approach, I think. So picture this, right? You start with like a simple bowl shape,
Okay.
very obvious lowest point, right?
Right.
Now imagine slowly morphing that bowl
Yeah.
into that complex landscape that you're actually trying to navigate.
Okay, so we're gradually introducing the complexity, giving our system time to adjust as we go.
Yes, exactly. If you do this slowly enough, the system, which in AQC is represented by qubits, they'll naturally stay at the lowest point throughout that entire transformation.
So we're essentially easing the qubits into the optimal solution without them getting lost in all the bumps and changes along the way.
Exactly, yeah. And this is where the polyspin method comes in.
Okay.
It simplifies how we even represent the problem for the qubits in the first place.
Okay.
So instead of dealing with this whole spectrum of continuous values, we
Yeah.
break it down into binary form, just using zeros and ones.
So it's like we're translating the problem into a language that these qubits can understand a little bit better.
Yeah, precisely. Yeah. It's a much more natural way for them to think about it. And this is where those polyspin matrices that you mentioned, they come in.
Okay.
They're essentially mathematical tools that let us express our problem,
Hmm.
those weights and biases that we talked about in terms of these zeros and ones.
So it's all about simplifying that information for that quantum system to really process.
Precisely, yeah. And because this method works so well with that binary representation, it's particularly well suited for these near-term quantum computers.
Okay.
These computers naturally, they think in terms of zeros and ones anyway. So it makes the whole process much more efficient.
So by speaking the quantum computer's language, so to speak, we're able to harness its power more effectively to reach those solutions.
Exactly.
But how does this actually translate into real-world results? I mean, did the researchers actually put this method to the test? They put this method to the test. Did they get any interesting result?
Oh, they did, yeah. The paper highlights two main examples. The first one is what they call a toy model, which is basically a smaller, simpler problem, just to kind of see. If AQC can handle a situation where you have multiple equally good solutions.
Okay, so kind of like finding several different routes on a map that all take the exact same amount of time to get there.
Exactly, yeah. And, a traditional neural network, it might just randomly pick one of those routes, whichever one it stumbles on first.
Right.
But AQC, it actually explores all of them simultaneously.
Mm.
It's not until, a measurement is made at the end and you force that quantum system to give you a concrete answer
Yeah.
that it chooses, so to speak, one of those optimal solutions.
So it considers all the best options instead of just kind of, like we were saying, getting stuck in that rut, just stumbling upon one.
Yeah.
That's really interesting. What about the second example? What did we look at there?
So the second example tackles a more, I guess, practical problem.
Yeah.
Image classification.
Okay.
They used what's called a binary neural network,
Okay.
meaning everything is represented in these zeros and ones, right?
Right.
And the results were actually really impressive. AQC achieved a perfect 100% accuracy in classifying images.
Wow. 100%. That's incredible. What kind of accuracy were the traditional methods getting for comparison?
Yeah, so the traditional methods, they still did pretty well. Don't get me wrong, like 80% accuracy on this particular task.
Okay.
But still, AQC demonstrated a significant improvement.
Yeah, that's a substantial difference. I mean, that kind of improvement could have huge impact on, any field that relies on image recognition.
Oh, absolutely.
But I'm guessing there must be some limitations here, right? Things can't be perfect just yet, can they?
Yeah, you're right. There are some challenges that, still need to be addressed. So while AQC really excels at finding these optimal solutions, and it shows, like, huge promise for these smaller scale problems.
Yeah.
Scaling it up, to work with these massive, complex neural networks that are being used today, that's still, that's a hurdle.
So AQC is like having a high-performance sports car, It can handle those tight corners and tricky maneuvers, but maybe not quite ready for that long-haul road trip just yet.
That's a great analogy, yeah. For AQC to really, hit the mainstream, we need to figure out how to make it more efficient for those larger scale problems.
Right.
And that's where future research comes in.
So we're still in those early stages, but the potential is certainly there, it sounds like.
Absolutely, yeah. This research opens up so many exciting avenues for, the future of AI.
Yeah.
Imagine a world where AI can solve these incredibly complex problems, like, designing life-saving drugs or revolutionizing material science, all while being faster and more efficient than, what we can even imagine today.
It's like we're on the cusp of a whole new era of computing where, those limits of what's possible are just constantly expanding.
Exactly, yeah. And the best part is, you don't need to be a quantum physicist to appreciate the impact this could have.
Right.
If quantum computers can make AI significantly better at solving problems, it benefits, everyone.
It's like how we don't need to understand all the intricacies of how a smartphone works to be able to use it in our everyday lives.
Precisely, yeah. So while we might not be, building quantum computers ourselves, it's pretty amazing to think that the technology that they're developing could revolutionize, everything from healthcare to climate change, in the coming years.
It really is kind of mind-blowing when you think about it like that. So for our listeners out there who are, eager to learn more about this, what would you say is the key takeaway from our deep dive today?
I think the key takeaway is this. While quantum computing might seem like something out of science fiction,
Yeah.
it has this very real potential to change the world as we know it. The way we train AI today could be fundamentally different in the not so distant future.
Right.
And that's incredibly exciting.
Yeah, it's like a whole new world of possibilities is opening up right before our eyes. Well, it's been fascinating diving into this research with you today. Thanks for joining me and really shedding light on this groundbreaking work.
Oh, it was my pleasure. Happy to be here.